So the basics of what we'll be looking at this week is just the idea that moving charges can induce a magnetic field. So they create a magnetic field, and that magnetic field can interact with other magnetic fields, creating forces. On the reverse of that, a moving magnetic field can induce current. Mostly what we'll be talking about this week is the top two of those. But the bottom one is something that can happen, and we'll look at a little bit more when we talk about windmills later this year. In a diagram you'll see in a moment, there's going to be it has a wire that is carrying a current of about 5 amps. And if you sprinkle iron fillings on the horizontal card and tap it gently, the iron filings will line up within that magnetic field. And there's a YouTube video that I have marked in your materials folders that you can take a look at and watch this happening. But just looking at what you have here, you have the current that's going through there. You have the iron filings on the cardboard, and then when you put that current through there, they align, showing where the magnetic field is. And if you were to take a compass and set it along there, the compass would continue to turn as it went around that field. So if we had a current that's coming out of the page here, and we see the way that the filings can align, if you watch the YouTube video that's in your materials folder, and if you look at that, the filings line up really nicely, but it doesn't give you much direction about the field. And so if I were to take a compass and put it right here just outside of where I have the lines drawn, you could put it in there too, but for the sake of seeing it, it would align in the direction of the lines at any point. So the compass would point this way here. If I were to take a compass and put it right here, it would align that way. If I were to take a compass, put it over here, and you can see what's going on with each of these. That at any point, it's going to align with what's happening around there, and it would continue around. You know, if I go here, obviously, it'd be between these two, so it would be like that. And so there's different ways that we can determine that based on the different rules that we have. So this just talks similarly to what I just talked about. At the bottom, though, it asks what would happen if you were to reverse the direction of the current. If that were to happen, it would reverse the direction of your lines as well, because if the current's going opposite, that magnetic field would set up oppositely too. Before we get too far, we need to talk about how field lines are represented for a magnetic field. Field lines will always be drawn very similar to the lines that we used for electric field, and they'll be drawn from the north to the south. And so if you were to take a compass and put it, if you were to take a magnet and put it in there, the magnet would point, the north would point where the field lines are going because it would be attracted to the south. And so you'll always have your lines from the north to the south. Two other symbols that'll show up and be important for what we're doing. Anytime you see an X, it means it's into the page. And when you see a dot, it means out of the page. When we're looking at it here, it indicates where the current is going. So the X means that the current is traveling into the page, and the dot means that the current is traveling out of the page on a given wire. At other points, we'll see the X and the dot indicating the direction of the magnetic field, but it still remains the same, that an X means it's going into the page and a dot means it's coming out of the page. So we can see in this picture that we have an X, so the current is going into the page, and we can see that the magnetic field is wrapping around there. In this one, we have a dot in the middle of the page, and so the current is coming out of the page. And you can see that the magnetic field is going around that current, but the direction of the field has changed because the direction of the current has changed from the previous picture. A couple of ways to remember this is that consider it to be an arrow that's been shot. And if you're standing there and you've shot the arrow into the page, you would see the tail feathers on that, created in the X going into the page. And if it were to be coming out of the page toward you, you would see the tip of the arrow that looks like a dot. And so that's just one way to kind of keep in mind of what it might look like and how it can be remembered. One of the other pieces to note is that as you get farther away from the center of those diagrams, the lines spread out farther, which means that your magnetic field is becoming weaker. And so just in general proximity, the closer you are to the thing that's producing the force, the stronger that force will be. So as you move out, it will be weaker, and that's indicated by the flux lines becoming farther apart. With this, we have something called the right hand rule, and the right hand rule helps us to figure out what's going on in a given situation based on where the current is and then where your magnetic field would be. And so with the right hand rule, you'll use your right hand. Even if you're left-handed, this is one that needs to be with your right hand. And for part of it, and there's several different kind of variations on what we're looking at, but for part of it, you'll take your thumb and it will become it'll go in the direction of the current. And then the way that your fingers wrap will be the direction of the lines of flux for your magnetic field. So if we go back to the image that I drew earlier, where we have a dot in the middle, and so the current is coming out of the page. So I would point my thumb in the direction that the current's going, coming out of the page. And so when I do that, it looks like this. And then my fingers wrap around in a counterclockwise direction, and you can see that my arrows will point counterclockwise as well. And so with the right hand rule here, I'd have the coming out of the page, my fingers wrap around this way, and that's how I would draw it. The other thing that could happen is if I had an X going in and my current was going into the page, I would reverse that, so my thumb would be going into the page and my fingers would wrap in the opposite direction. All of these arrows would flip. So in this next part, we're going to look at what the magnetic field is in a flat coil when you have a current that's running through it. And so the diagram we're going to look at next will indicate that, and we're going to look at a few different pieces that go along with that. So if we look at this, we can see a few different things that are going on. First of all, we have our magnetic field coming through here. Our arrows are pointing through to the far side of the page here. And so we know that we would be going from the north to the south here. Second thing is that we have our current that's coming around the coil. It's going from where we're looking, it's going in a clockwise direction. And what we can do is we can figure out a few different ways in that the line was drawn here. So if we focus on just this point here, just this single point, we can use the right hand rule as we currently know it, and the current's going into the page, and so our hand would wrap around and it would be going here in a clockwise direction, and we would be seeing the circles that we have here. So the thumb would be going down, be wrapping around this way, and our lines drawn that way. If we come over here, we have the current coming out of the page on this spot, so it's going up. And if we coming out of the page, we wrap around. Now we're wrapping counterclockwise, and you can see that the arrows here are going counterclockwise right there. The other thing that happens is we have our magnetic field that's going through here. Another way that we can indicate that is to reverse the way that we have our right hand rule. Instead of having our thumb represent the current, we're going to have our fingers represent the current because we're going in a circle. And so I'm going to have my fingers wrap around here as if they are coming out of the page and going into the other side of the page. So they're wrapping around here, and my thumb is pointing over to the right here. And with the fingers wrapping this way, you can see that the magnetic field is going that way. If we were to reverse this and have the current coming out here and going in over here, we would move our fingers in the direction of the current, so we'd be going across the top here, and our thumb would be pointing to the left, and we could see, and then it would flip the direction of those arrows, and it would be heading that way. In a solenoid, it's very similar to a single wire that's wrapped around in a loop through the page like we just saw. And so we're going to take a look at that and how that works here. So a solenoid is similar to a single wrap that's through a page, and this one, what happens here is you have a whole bunch of loops that are going through that page. And with a solenoid, we can use that second way of doing the right hand rule, where our fingers are going to wrap in the direction of the current. So if I take my hand and I look, and the current is coming from the back toward the front, you can see that my thumb is pointing over to the right here. And so if we look at the way that the current's going that direction, so our magnetic field would be headed to the right like it's drawn here. If we were to take this and look at it at a single wire, we could see that like right here, look right here, it's going into the page, and so it wraps around that way, and you can see that the lines are drawn in a clockwise fashion. And then over here where it's coming out of the page, it's coming around this way, and they're drawn in a counterclockwise fashion. So the rules still apply, but you have a lot more wires going around and several more loops. The other thing that happens then, if you have a solenoid like this, then it can also behave similarly to a bar magnet, and that can be helpful in various situations. So just a couple of things to be thoughtful in this. First of all, it does behave like a bar magnet when you have something set up like this. Inside of that solenoid, you can see that the lines of flux are really close together, and they'll be parallel and equally spaced, and they'll be, like I said, close together. And with that, you have that because you have a strong field in there, and it's a uniform field throughout the whole inner part of that solenoid. And as with other things that we've looked at as we've been going through this, if you reverse the direction of the current, the magnetic field also reverses. And this is just a diagram of that second way that we were looking at the right-hand rule, where we're using the fingers in the direction of the current, and then the thumb is in the direction of the magnetic field. And when we're doing that, again, you have to remember that it is always, always, always the right hand. Up until this point, we've been looking at the way that a current can induce a magnetic field. And what we're going to be looking at in what we have set up here is how inducing that magnetic field in a fixed magnetic field causes forces. And so this is our basic setup for what we're talking about here. We've got a current that's coming through. It goes through a copper rod, it goes through an aluminum rod, and then back through another copper rod. And copper and aluminum on their own are not magnetic. And so it allows it to not have other magnetic fields that are playing into it. And so the current comes through here, and this aluminum rod is not fixed. It's loose to move back and forth in any way that it chooses to, depending on what kind of force is being put on it. And so the current comes through here, and by the current going through the aluminum rod, it induces a magnetic field around that aluminum rod. Well, if you have two magnetic fields, they will interact with each other and create a force depending on which direction things are being pushed. So if you look at this, if we look at the direction of the current, we can take and figure out what's happening with the direction of our magnetic field around the aluminum rod. So if we take our thumb and it's pointing to the right, it means that our magnetic field is coming around, and it's coming up the back and around the front of that aluminum rod. Well, that magnetic field is going to be interacting with the field that's created by the fixed magnet there. And because of that, we'll get a force. Let's look at what's happening in this situation from the side. We have the current that's coming along that aluminum rod. And from the direction that we're looking at, we've got it coming out of the page here. So what we're looking at is now we're turning this, so we're looking at it from this direction here, and it looks like this. So we've got the current coming out of the page, and if we take and we make our lines, we can see that the lines of flux here are going around in a counterclockwise direction. So what happens here is our fixed magnetic field is going from here to here up, and so if we focus just right here, the fixed magnetic field's going up, the magnetic field at this point is going down, so it cancels out, they cancel out each other without having any magnetic field right in this spot to the left of the rod. On the other side, however, we have it going up right here, and because the magnetic field that's going around the rod is going up, and the magnetic field from the fixed magnet here is going up, it adds to the magnetic field that's already existing in that situation. And so because of that, it creates a force that's going this way away from that. Sometimes people like to think of it of like a slingshot, like they're pulling it back and you've got a whole bunch of rubber bands here. When you let it go, it pushes that way. And so that this occurs because, like I said, on this side, we've got at this part, we have the magnetic field that's going down, and it cancels out part of the magnetic field that's going up. And on this side, the magnetic field from the rod is also going up, and then the magnetic field from the fixed magnet is going up, and so they add to each other. And because of that imbalance, it creates a force that's heading this way. So we don't have to draw all of that every time we need to figure out what's happening with the force. We have another right-hand rule that we'll be looking at with this. So when you have a current that's traveling in a fixed magnetic field, you're able to figure out where the force is going by using another variation on the right-hand rule. In this situation, you'll put your fingers in the direction of your magnetic field. Your thumb will be the direction that the current is flowing. And when that's happening, the place that your palm is facing is giving the push. So the palm gives the push in the direction of the force. So when they have this set up here, they show that the magnetic field is heading over to the left, and the thumb is going into the page. So the current's going into the page, and so then the palm is facing up. And so the push would be up from where you have that. So it would be up. It's always going to be perpendicular to both the magnetic field and the current. So let's use the situation that we had before and apply the right-hand rule to it. We have a dot in the middle here, and that indicates that the current is coming out of the page. And so I'd have my thumb pointing up in the direction of the current. My fingers go in the direction of the magnetic field, so fingers and field. And so that's going up, so my fingers are pointing up. And so the way that I would push with my hand would be over to the left here, and that's the direction of the force. You can think about a force is a push, and so the force would be applied that way, pushing that rod over to the left. Sometimes you'll see a setup that looks like this, where you're going to have a bunch of X's on there, and that will indicate that you have your magnetic field. And because they're X's indicate that something's going into the page. And so in this situation, my magnetic field is going into the page, and so my fingers would go into the page. And for the sake of being able to change things around, I'm going to use a dart indicating the direction of my current. And so if I have this dart and my current is going up the page, so my field is going in, so my fingers would be going in, and my thumb would be pointing up the page. That means the force would be over to the left. Now, if I were to switch the direction of my current and have my current going down the page, my fingers would still stay in because the field's still in. And now my thumb would be pointing down the page, if you can see that. And then I'm pushing over to the right. So by changing one of the pieces, you end up changing the direction that that force is going. Again, if I were to rotate this and it were to be going, the current were to be going through this field, heading to the left, my fingers would be into the page. My thumb would be pointing to the left. Sorry, I had that backward. Thumb would be pointing to the left, so the force would be pushing down like that. And if I were to reverse this, fingers would be into the page, thumb would be heading toward the right, and the force would be going up the page. So depending on what you have, if I were to have it going something like that, going into the page like this, I'd have a direction like that. If I flipped it down here, again, into the page, thumb is in direction of the current, and it would be moving like that. And so as long as you have this going into the page, and then this can go in any direction, it still ends up being perpendicular to that. So in review, your fingers point along the direction of the magnetic field. So from north to south, it's in the direction that the arrows are drawn. Your thumb will point along the electric current, so from positive to negative, and your palm will push in the direction of the force. Now I'm going to talk about current next, and the whole idea of conventional current and actually the motion of the electrons in there. It ends up being goofy. Let's talk about current for a minute. Current is a little bit goofy because originally scientists believed that the current was a movement of a positive charge that was moving around. And so with a battery or a cell of some sort, you would have your positive charge being the long line, the negative charge being the shorter line. And so they said, well, positive repels positive, so the current would come out this way, and the current goes around. They did a whole lot of measurements with current, nothing fancy, but current was believed to go from positive to negative because it was believed to carry a positive charge. Over time, they realized that it wasn't a positive charge that was being carried, but instead it was an electron. And by the movement of electrons, well, electrons are negative. And so the motion of those wasn't going from positive to negative, but instead was being repelled by the negative and pushing around toward the positive. So scientists had a situation to deal with at that point. Everything that they had done had been in relationship to current going from positive to negative. But the reality that they were finding was because it was electrons moving, they were going from negative to positive. And so they could either go and switch everything at that point, or say, yep, we're going to keep current as it is, and we just will know that it's actually the flow of electrons is actually backward from what we're going to talk about it, which probably made good sense at the time because it meant they didn't have to change too many things. Reality is now at this point, we just look and say, what? Why did you do that? So the things to know is that current is going to be drawn and discussed going from positive to negative. We call that conventional current. Conventional current is with the idea that current is positive to negative, and that's how we put it into the different things we're looking at. However, the flow of electrons is always going to be opposite that. And so electrons have a negative charge, and so they are actually flowing opposite what we'll discuss the current as being. And so that difference between the conventional current discussion and then the flow of electrons, we have to know that. Now, for a lot of things that we do with the right-hand rule, when we're talking about magnetic field, current, and force, we talk about putting our thumb in the direction of the current. And so if the current is going up the page, we would put our thumb in the direction of that current going up the page. Well, that is assuming that we also then know that our electrons are flowing opposite that. So it's not a problem if we're just talking about current, but in some of the stuff we'll look at, we'll talk about having an electron, a single charge, or a proton move up the page. And if the proton is moving up the page, we can treat it just like current. And we would put our thumb in the direction of the proton motion there. However, if it is an electron, remember electrons flow opposite of the current. So if you have a single particle that's an electron or has a negative charge of some sort, and it is traveling, if they say that it's traveling up the page, that's cool. But it would mean, if it were to be part of current, even if it's not, that we would count that as current heading in the opposite direction. So if the electron is going up the page, you would put your thumb would be pointing down the page. This is the only time that you would have to do something different with that. And it comes from this idea that conventional current is still discussed as going from positive to negative, even though the flow of electrons goes from negative to positive. So when you're using your right-hand rule and current is going up the page, your thumb would just go with the current. If you're using your right-hand rule and a proton is going up the page, that would be similar to current, and you would keep your thumb going up the page in the direction of that proton. The only time you have to do something different is if you have an electron that's traveling. And what happens is, because the electron is moving that way, it would be assumed that the current, actual current that we'd be measuring and talking about, would be facing down. So if you're using the right-hand rule in a situation where you have an electron going up, you need to flip your thumb going down to go opposite the direction of that electron and in the direction that the current would be considered there. I know it's goofy. So how do we calculate the force that's actually acting? So we can figure out where the force is going to be using right-hand rules of various types. And with this now we can look at how to actually calculate it. And so we have a couple of things that are going on here. The force on a conductor is in a magnetic field is directly proportional to these three things. The magnetic flux density, it's represented with a B and measured in Teslas, the current, and then the length of the conductor in that field. And we'll look at that in a minute. Now, directly proportional is always nice. So if you have a stronger magnetic field with the flux density measured in Teslas, you'll have more force that's created. If you have a stronger current, more force. If you have a longer wire, you have more wire in there, more force. Now the assumption that's made with this is that they're all at a 90-degree angle to each other. And so there's one more piece of the equation that we'll add in to figure out what's happening if they're not at a 90-degree angle to each other. And to do that, we can look at this diagram here. If you start all the way over on the left, and you look at the current that's going perpendicular to that magnetic field, we would have that going 90 degrees. Now, what happens, and we've done this in other situations, is any part of it that would be going 90 degrees when you break it down into x and y components is the part that's calculated in the way of that force. And so in order to do that, you can see that as it moves to various angles, it gets down all the way to the point that you have that theta is equal to 0, and it's in line with that magnetic field. If it's in line with that magnetic field, it's not going to do anything to interact with it, and it won't change the force at all. And so we have that theta in there, and that ends up giving us a different equation, or an addition to the equation. We'll add a sine theta to the end of the equation because that would be able to take and give you what you need that's heading in that direction that's perpendicular to the magnetic field. And so if the line itself is already perpendicular to the magnetic field, then you'd have a sine of 0, and that equals 1. And so you would just have the B, I, and L there. If it is at an angle, by adding the sine theta, you're figuring out which component is perpendicular to the magnetic field, and then that's the part that calculates into that force. One thing to point out here is that the magnitude of the force is going to be dependent on that angle, but the direction of the force is not. And so if you take one that's at, 45 degrees or something, and the size of the force is reduced because it's not completely perpendicular to the direction of the magnetic field. However, the direction of that force isn't. And so keep that in mind as you're setting things up and making those calculations. So if we go back and look at these, let's say we look at I don't know, whichever one in the middle. For each of these, it doesn't matter where they are along those different angles, the direction of it would still, if I take it and I use my right hand rule, my current is going up the page, my magnetic field is going to the right on the page, and so my push would be down into the page. And so it wouldn't matter the direction of that, the push would still be down into the page, and then the direction of that would adjust whatever magnitude you have on that force. So if we rearrange this, we can say that B is equal to F over the current times the length. And what that means, it means the current is 1 amp and the length is 1 meter. And in this case, B would have the same numerical value as F, which then can give us this definition that we have the magnetic flux density is the force acting per unit length on a wire carrying unit current, which is perpendicular to the magnetic field. And so when we look at the unit of B, which is the Tesla, 1 Tesla is equal to 1 Newton per amp per meter. This means that when we're talking about a Tesla, we're saying it's the magnetic flux density that produces a force of 1 Newton on each meter of wire carrying a current of 1 amp at 90 degrees to the field. Now, we don't always have a full current that's heading through a magnetic field. Sometimes it ends up just being a single charge. And so we're still going to have a similar situation, and we'll have, in this case, the force is proportional to the magnetic flux density, the charge on the particle, and the velocity of the particle. And so the equation on this looks like this, where we have the force in newtons is the flux density times the charge times meters per second. And so again, it'll have, and this will pop up in a moment, it'll have the sine theta on the end, depending on the direction that ends up being in relationship to the magnetic field. And so your equation looks something similar to this, because as long as it's perpendicular, you would have that full force. But if the motion of that particle ends up being at some angle that's not perpendicular to the direction of the magnetic field, then you would include that sine theta in there to figure out how much of it is perpendicular to that direction of the magnetic field. And so again, just a reminder that you'll still use the right hand rule, but if it is an electron that is moving through that field, that the direction of the thumb would be opposite the direction of that electron motion because of the way that we define and work with conventional current.